Today's topic, there's really actually two topics. We're going to talk first about liquids, and then we're going to talk in general about fluids. We're going to define and discuss some properties of liquids. We're going to start out with maybe its most important property for some purposes, and that is that it has a definite volume. In other words, another way of saying this is it's incompressible. This means that as you increase the pressure on a liquid, the more you make the pressure, not much happens to the volume. The volume pretty much stays the same. By contrast, we learned in the last set of notes that gases respond a completely different way. For a gas, when you increase the pressure, the volume changes dramatically. Liquids have this property in common with solids, but they definitely, you can see, don't share this with gases. Another important property of liquids is that they have an indefinite shape. This is a property that they share with gases. Another way of saying this is that they're fluid. It means they can flow, or they will take the shape of their container. It's another property of liquids. The fact that liquids are both fluids and incompressible make them really useful for things like brake systems or hydraulic systems. Another property of liquids is what we call cohesion. Cohesion is the attraction between individual particles of the liquid. For example, water exists as a liquid because a water molecule and another water molecule have a strong attraction for each other. So that's water. Water exists as a liquid because of strong cohesion. On the other hand, oxygen, one oxygen molecule and another oxygen molecule have a very weak cohesion. And so at room temperature, they fly apart from each other and they exist as a gas. Adhesion is another property of liquids. Liquids will not only attract themselves, but they'll also be attracted to the particles of the surface of a solid. This results in something called wetting. If the particles of the liquid are attracted to the surface of the solid about as strongly as they are to each other, well, the liquid will spread out and wet the surface. Let's take a look at that. Okay, here's a guy, he's going to pour some water on a clean metal surface that's painted, and you can see that there's strong adhesion here. The water spreads out over the sheet metal, and it's attracted to some particles in the paint. So you get this surface wetting phenomenon. That's stronger adhesion than cohesion. Now he's going to pour water over this other car, and this car has a different surface because it's been coated with wax. As he pours the water over the fender, you can see that it doesn't do the same thing it did on the other car. Instead of wetting the surface, instead of spreading out and forming a sheet, the water just runs right off. It doesn't have a very strong attraction for the car fender. It has a much stronger attraction for itself. Another property of liquids is viscosity. Sometimes people commonly call viscosity thickness. It's really a measure of the rate of flow of a liquid. Let's take a look at this little video that'll show us a picture of several different liquids with different viscosities. You can see that the one on the right has got a lot less viscosity than the one over on the left. It's flowing much more slowly. Different liquids naturally have different viscosities. It's a property of liquids. And it depends on cohesion. Strong cohesion is typically going to mean slow flow or high viscosity. In general, viscosity decreases for liquids as the temperature increases. In other words, as it gets hotter, the liquids tend to flow better. As it gets colder, they tend to flow poorer. This is where the old saying, slow as molasses in January, comes from. Molasses gets really thick when it's cold out, like in January. Another property of liquids is something called surface tension. It's a sort of a skin, a network of molecules that forms on the surface of a liquid. A few places where you can see that, well, here's one of the places you can see that. This water beetle, it's called a water strider, I think, is actually walking on that little network of molecules. You can look at the places where its feet are placed on the ground, and there's a little depression in the water, almost like a little hammock, and the water strider walks on that. Another place you see that is in the formation of droplets. Looking at this slow motion picture of droplets coming out of a water faucet here, you can see that the water droplets are forming spheres. They're sort of creating a shell. That's surface tension. Well, here's how surface tension works. If you look at the outside of a droplet, inside we've got all these molecules. Every one of these dots represents a molecule. A molecule in the middle of the unit here, is attracted pretty much equally on all sides because it's surrounded by all kinds of other water molecules that are attracted to it. if we're talking about water. And so this particle experiences no net pull anywhere. But if you look at a particle on the outside surface, well, it's attracted to particles that are also on the outside. It's attracted to particles that are on the inside. But there aren't any particles out here on the outside for it to be attracted to. So this particle does experience a net pull towards the inside. And that's going to be true for this one, and this one, and this one, and all the particles on the surface. And that's what surface tension really is. It's this net pull towards the center of the circle. That can be broken up by putting things in there that break up the bonds between the particles. Those are called surface acting agents, or surfactants for short. Here's another property of liquids. It's called capillary action. Capillary action is when you take a tube, typically a thin tube, and you put it in a liquid, it'll either elevate in the liquid or it may depress in the liquid because of the competing effects of adhesion and cohesion. If adhesion is bigger than cohesion, then the liquid will be more attracted to the glass walls of the tube and the liquid will rise. So we would see something like this with water, for example, would be a good example of something that does capillary rising. So the level of the water will rise up into this tube if the tube is placed in the water, and you'll have a liquid level up here somewhere. If the cohesion for the liquid is bigger than the adhesion, like with mercury would be an example of that, then you're going to get depression. It's actually going to go down below the level of the water or the mercury on the outside. So sometimes capillary action is a fall like this, and with water it's a rise because the cohesion is. Here's a property of capillary action. The height of the capillary action is inversely proportional to the diameter of the tube. So we could say the height is proportional to 1 over whatever the diameter is. So let's say, for example, that this thing has a diameter of 1 millimeter. The height that the column might rise would be up to 10, let's say. Goes up to there. Well, if over here we have another capillary tube that has a diameter of 10 millimeters or a centimeter, we're not going to see it go up very far. We would only see it go up to 1, inversely proportional. 10 times bigger diameter, 10 times smaller height. Another factor that affects the height of the capillary action, and this goes for elevation or depression, is temperature. The height of capillary action increases with increasing temperature. So let's say that this is cold, and let's say that over here we have some liquid that's hot. Here we might see this elevation. Here we're definitely going to see a bigger elevation. Now this isn't a linear relationship, so we can't say, that there's any kind of a direct proportionality. It's nonlinear. But hotter temperatures do increase the height of capillary action. Another property of liquids is thermal expansion. You can't make them get smaller or bigger very much by compressing them or releasing pressure, but you can get them to change volume a little bit at least by changing the temperature. Thermal expansion can be expressed this way. The volume of a liquid will increase with increasing temperature. So you increase the temperature and the liquid's volume gets bigger. This is a linear relationship for most substances, for most liquids. And the relationship goes like this. The change in volume over the original volume, that ratio, is equal to a number called beta. This is a characteristic of the substance itself. It's called the coefficient of thermal expansion times the change in temperature. So this is called coefficient of thermal expansion, and it's different for different substances, so you'd have to look it up in a reference, and if you didn't have it, you could probably find it by experiment by using the same relationship. Well, let's try an example problem here. We've got a thermometer. It's filled with a mercury column. The diameter is given. The height is given initially when it's 10 degrees C. The total volume of the mercury in the thermometer is given to us. And we're supposed to calculate the height of the column of mercury when the temperature goes up to 40 degrees C. And beta, the coefficient of volumetric expansion here, is given for mercury as well. Let's go ahead and set this up by drawing ourselves a before and after picture. Here's my before thermometer, where it's 10 degrees C. And here's my after thermometer. In my after thermometer, it's 40 degrees C. I got a mercury column in here that comes up 8 centimeters, it says. And of course there's mercury down here as well. Mercury isn't really red, but I'm looking for contrast. At 40 degrees C, we all know, because we know how thermometers work, the column is going to be higher than it was before. So here's our height, initial height, 8.0 centimeters. It says the diameter of the column here is 0.2 millimeters. Well, that would be 0.02 in centimeters. Well, we want to know what is the change in height here for the 40 degree temperature. Well, it's going to have a change in height because it has a change in volume. And the volume of a cylinder is pi r squared times h, area times h. Because glass encloses the radius, it's not possible for the volume to expand that way. It has to expand in height. So any change in volume that's experienced has to be experienced as a change in height. So change in volume corresponds to change in height. So our change in height, well, that's just going to be the change in volume divided by pi r squared. We can find change in volume because we just learned an equation for that. Our change in volume over our volume is equal to beta times change in temperature, where beta is the coefficient of volumetric expansion. So that means change in volume is original volume times beta times change in temperature. Well, beta is given to us. The change in temperature is the difference between the starting and ending temperature. That's just 30 degrees C. So let's put some numbers to this. Change in volume is equal to the original volume. Well, it said the original volume was 0.357 cubic centimeters. Beta, well, beta was 1.82 times 10 to the negative fourth, and the unit here is per kelvins. And then our change in temperature is 30 degrees C. But we could say 30 kelvins. Degrees C and kelvins are interchangeable when it comes to differences because they're the same size of a degree. So kelvins drop out, and our change in volume will have units of cubic centimeters. When you do the arithmetic, the answer is 0.0019 cubic centimeters. Well, the reason we wanted to do that was so that we could find delta H through this equation here. So we're going to take our delta V and divide it by pi r squared. Let's set that up. Delta H is delta V divided by pi r squared. Well, we've just calculated delta V to be 0.0019 cubic centimeters. That's divided by pi times the radius squared. Well, the diameter is 0.02 centimeters, so this will be 0.01 centimeters, and that's going to be squared. The units on delta H will be square centimeters divided into cubic centimeters, and that's just centimeters. The change in height is 6.04 centimeters. Let's just round that up to 6 centimeters. So the final height at 40 degrees C is going to be the 8 that it started with plus 6. It's going to go to 14 centimeters high at that temperature. For most liquids, this thermal expansion is a linear function. But for water, it's not linear. And if you zero in on its graph of volume change versus temperature change and get right down near the freezing point, this is pretty close to zero, you can see as it gets closer and closer to the freezing point, the volume actually gets bigger. Almost nothing else does this. Most things start out at their freezing point and just get bigger and bigger and bigger as it warms up. Water doesn't do that. And that's really weird, but it's also very good, because if it wasn't for the fact that water gets less dense when it freezes, water would freeze from the bottom up. And we would never be able to survive a winter if we didn't have ice over the top of our water, because all the aquatic life in every pond and lake and stream would die over the winter. So it's a very unusual but useful feature of that particular liquid.